Welcome to Empowered Learning. This is the final video in the video series for improper integrals. So in this video, we will be using the direct comparison test, limit comparison test, or other means to be able to help us figure out whether these improper integrals that we are going to be considering will be convergent or not. Okay. And again, remember that when an improper integral is convergent, that just means that either if we do it by hand or if we do it via computer or numerical integration, we will be able to get some numerical real number answer for the definite integral. If we get something like positive infinity, negative infinity, or does not exist for the result of the improper integral, then we know that that particular improper integral diverges. So for this first example here, we are considering the definite integral from 0 to 2 of 1 over 1 minus x squared dx. Okay, and so in looking at this, we see that our integrand is just 1 over 1 minus x squared. Okay, we know that this is an improper integral because if we plug in 1 here, we'll get 0 in the denominator, and we also realize that 1 is in between 0 and 2. So this is a type 2 type of improper integral where essentially our function has a vertical asymptote type of discontinuity in between the numbers for the limits of integration. So in noting that, let's also note that our integrand could also be rewritten this way. And notice that if we dropped that plus 1 there, then we would end up getting a function that looks like this. And because of the fact that negative x squared ends up actually being a number that's going to be smaller than negative x squared plus 1, then what that turns out to be is that 1 over negative x squared is going to be a number that ends up being larger than 1 over negative x squared plus 1. Okay? So essentially here, if the denominator is smaller, if we're comparing these two, if this denominator is smaller than that one, in other words, the denominator negative x squared is smaller than negative x squared plus 1, and the numerators are the same, then that means that the expression 1 over negative x squared is going to be larger than 1 over negative x squared plus 1. Okay? So here we're going to name this our big function, and we're going to name this one our little function. And let me make that look a little bit better here. Okay. This is going to be our small function. Now, according to the direct comparison test, I'll write this here, we either need to show that the big function, when we do the improper integral for it here, using these same limits of integration, the integral of our big function has to converge, or the integral of our smaller function has to diverge in order for the direct comparison test to work. Okay? Now, since the bigger function is easier for us to work with, we're going to see if, in fact, if this function, or this particular improper integral, we want to see if that is actually going to converge. Okay? So that's our goal. All right, so let's see. So if we want to see if this converges or not, we just basically need to take the antiderivative of this. And so to kind of save some space, I'm just going to rewrite this as x raised to the negative 2. And if we were to take the antiderivative of this, this would end up being essentially a negative 1 over x. And we would evaluate that, of course, from 0 to 2. But since this is an improper integral, we have to write some limit notation stuff in front. So let's go ahead and do that. So since 0 is the issue or the limit of integration here that makes, well, sorry, it's actually 1 here. But if we're looking here, 0 is going to be the problem, because remember, this is like 1 over x squared, and plugging in 0 here would make the denominator of x raised to the negative 2 be undefined. So we're going to write limit as a approaches 0 from the right of integral of a to 2 of x raised to the negative 2 dx. And so now we can go ahead and write limit as a approaches 0 right of a minus 1 over x, and that gets evaluated from a to 2. So this will end up being a minus 1 over 2 minus a minus 1 over a. And of course, that subtracted negative is the same as addition here. Okay. And of course, if we were to plug in 0 for a, then of course that 1 divided by 0 is going to be infinity in terms of limits, which means all of this is infinity. So we see that this particular improper integral actually diverges. Okay. Now, what does this mean? This means that the direct comparison test can't be used. Okay. So remember here that for the direct comparison test, if the integral of the big function is convergent, then it means that the integral of the smaller one is also. But if the integral of the smaller function is divergent, then it means that the integral of the bigger one is. And so we chose to go with the big one. We saw that that didn't work. Okay. Now, all hope is not lost, because we can actually use this result to help us out, but we are going to have to employ the limit comparison test to be able to get us out of this hole here. Okay. So according to the limit comparison test, we have to know things like, hey, for this interval of x values that we are evaluating this improper integral on, does both of the functions lie above the x-axis? Is the function going to have either horizontal asymptote or vertical asymptote? Okay. Now, our integrand here does satisfy those requirements. Okay. So the only other thing that we are left to do here is to figure out, if I take the limit as x approaches infinity of my big function divided by my smaller function, will this result end up being a real number that is finite and positive? Okay, meaning, am I going to get something, a real number that's in between 0 and infinity? Okay, if I do, then I can use the limit comparison test, which basically says that the improper integral for both the big function and the small function are either both going to be divergent, or the improper integral for the big function and the smaller function are both going to be convergent, depending upon if my functions f and g and the corresponding improper integrals for that meet the conditions of that limit comparison theorem. And so, like I told you before, our integrand does meet those conditions here. So all we need to see is, are we going to get a corresponding value from this limit that is going to be something in between 0 and infinity. Okay, so if we evaluate this limit here, we'll see that we can rewrite this as a negative, and this should be x squared or minus x squared plus 1 over x squared. And if we go ahead and take care of this negative here, I could make this first term positive and the second term negative. So it actually come and do this like this. So that way we don't have to worry about the negative sign anymore. Okay. So we have that. Then, of course, this will now look like 1 over 1 over x squared. Plug in the infinity for x. That goes to 0. And we see that we get 1. And of course, 1 is a number in between 0 and infinity. So this does meet the conditions of the limit comparison test. Okay. So we know that from here, what this is telling us is that our original integral that we were trying to figure out whether it converges or diverges is actually going to diverge, because the improper integral for the bigger function that we were dealing with here diverges. Because remember, either both have to diverge or both have to converge. And since we use the direct comparison test to show that the improper integral that we actually evaluated, which was the improper integral of the bigger function, actually end up diverging, then we use a limit comparison test as a follow-up to make sure it met those conditions, so that we can also say that our original improper integral that we were trying to solve, or that we're trying to evaluate rather, we saw that it was also divergent. Okay. All right, so let's look at our next example. So for our next example, I'm asking you to use the limit comparison test here, and I've already worked this one out. So the main thing here is I'm wanting you to start off with the limit comparison test so you can kind of see how this works if you do that. But also I want you to recognize that this particular improper integral is very, very close in comparison to this one. Okay. Or if I write that another way, it's going to be very close to this one. Okay. And of course we know that this particular improper integral will diverge. We know that because this value here of p is less than or equal to 1. So of course this diverges. And so we want to try to do what we can to use this fact as quickly as possible. Okay. So we see here that for this particular integrand here, which is 1 over x squared minus 1, 1 over square root of x is a closely related function to it. And of course, 1 over x squared minus 1 is a function that is larger than 1 over square root of x for all values of x from 4 to infinity. Okay. So we also know that both of these functions here would lie above the x-axis, above or on the x-axis. Well, really it should be above the x-axis for values of x that are greater than or equal to 4. And so because of that, this automatically meets the conditions for the limit comparison test. Okay. So here we can let f of x be our original integrand and g of x be the closely related function. And here we can just do the limit of a quotient of those as x approaches infinity. And of course, you see when I work this out, the answer that we get here is 1. And since 1, of course, is in between 0 and infinity, the limit comparison test says that both either this function, this improper integral and this improper integral either both converge or diverge. And since we've already noted here, and I've done it up here, but I've also written it out, that since this particular improper integral diverges, what that means here is that the one that we originally had to figure out whether it converges or diverges will also diverge. Okay? So we see how using the limit comparison test kind of just cut to the chase and gave us the answer that we needed to know. Okay? So since we know that this particular integral here, improper integral, is going to diverge, that means we don't need to waste time trying to figure out what the answer to it is, because we won't be able to find it. Okay. All right. So let's look at the next example here. And so the next example is same problem, but now we're using the direct comparison test. Okay. So using the direct comparison test actually gets us our answer faster because of the nature of what our integrand is like. So let's recall here that if we look at our integrand and we compare it to 1 divided by square root of x here, remember that the original integrand is actually larger than 1 over square root of x, or it's larger than 1 over x raised to the 1/2. So according to the direct comparison test, if the smaller function is, if the integral of the smaller function is divergent, then it means the integral of the larger one is as well. Okay? And so here, remember that if we're going to consider this particular integral, it diverges because 1/2 is less than or equal to 1. Okay? So here, what I'm going to do is say it like this. So I'm say note that this particular improper integral diverges because 1/2 is less than or equal to 1, which means here that this particular improper integral will also diverge via the direct comparison test. Because remember, if improper integral of a smaller function diverges, then improper integral of a larger function also diverges. Okay? All right, so let's look at example H. So example H, we have the improper integral of 2 over t raised to 3/2 minus 5 of dt evaluated from 4 to infinity. Okay, and of course here we can rewrite this in radical form, and we know that our actual integrand here is closely related to 2 divided by square root of t cubed. Okay, and so of course, since this is a minus 5 here, that lets us know that the original integrand is going to be a function larger than this closely related function here for values of t that are 4 and higher. So remember here that our special case improper integral is convergent for values of p that are greater than 1. Okay. Notice here that 3/2 is greater than 1. So we know that in this case that our smaller function here, remember this is the smaller function, our smaller function, we we know that its corresponding improper integral is going to be convergent. Okay. Now, because of that, we are going to use the limit comparison test. Okay. Now, I'll write this out just to make sure that it's clear. So we can't use the direct comparison test in this sense, because remember, the direct comparison test says that if the improper integral of the bigger function converges, then we know that the smaller one will converge as well. Or if the improper integral of the smaller function diverges, then that means that the improper integral of the bigger one diverges as well. Okay, so we don't have that situation here. What we have is that the smaller function is converging. So that forces us to use the limit comparison test because it's one of those two other situations that I talked about in the part 4 video. Okay. So to use a limit comparison test, we just take the limit of the ratio of the two functions, the larger one and the smaller one. Of course, this is the larger one, that's the smaller one. You could flip it and do it the other way, really doesn't matter. So when we work this all out, and I'm not going to go through the gory details on that, we see that we get 1 here. And so what that means in terms of limits is that both of those functions grow at relatively the same rate. So that's why the limit as t approaches infinity of the quotient of those two functions ends up just equaling some real number that is in between 0 and infinity. Okay. So because of that fact, we know that our original improper integral that we were considering, which was way up here, we know that the original one is going to converge because the limit comparison test says that if our functions and improper integrals meet all these conditions here, then either both improper integrals converge or they both diverge. And since we know here that, again, the improper integral of the smaller function is going to converge and the conditions for the limit comparison test are met, that means that this particular improper integral, which is the original one, is also going to converge. Okay. So for our next example here, we have the improper integral of square root of x raised to the 5 plus 8, all that over x cubed, and we're evaluating that from 1 to infinity. Okay. So we want to figure out whether this particular improper integral is going to converge or diverge. So the first thing that should jump out at you here is that we could find a similar function to our integrand. So of course our actual integrand is this. A closely related function to this will just be square root of x to the 5th over x cubed, which, if we rewrote this, would be x raised to the 5 halves minus 3, and 3 can be written as 6 halves, which is x raised to the negative 1 half, or could be 1 divided by x raised to the 1 half. Okay. All right. So here, the two functions that we want to consider here will be this one and will be this one. Now, since if we look here and here, the only thing that's different is this plus 8 inside of the square root. And because of that, we know that the square root of x squared, square root of x to the 5 plus 8 divided by x cubed, that is going to be a bigger function than the one that we said was closely related to it. Okay. So here our goal is since this is the small function and this is the big function, we have to ask ourselves, we want to consider this particular integral here. So does it converge or diverge? Okay. And the easy answer to this question is that it diverges. Okay. Since we know 1/2 is less than or equal to 1, this implies that this particular integral here diverges. And so by the direct comparison theorem, we know that the larger the improper integral of the larger function is going to also diverge. Okay, and so that's all we have to do for that. Now, we weren't asked to figure out what the actual value of this would be. If we did, we still can find it anyway. So there's no point in trying. And now we know why. Okay. So for our final example here, we see that we have the improper integral of 1 plus sine x, all that over x squared dx, and we're evaluating it from pi to infinity. So again, what we want to do here is not try to evaluate this particular improper integral. We just want to figure out whether if we tried to evaluate it, would we actually get some real number numerical value? Okay, and another way of saying that is, will this improper integral converge? If so, we would get a real number value for the improper integral as an answer. If not, then it would diverge. Okay? So we notice here that our integrand is 1 plus sine of x over x squared. Okay. Now, why did I put that there? Now, one thing that we do know is that sine is going to vary in between -1 and 1, depending upon what values of x we have. So here we know that everything is going to bounce in between -1 and 1 here. Now, if we want to get specific, we know that, for instance, sine of pi, we know that is going to be 0. Sine of 3 pi over 2, we know that that will be -1. Sine of 2 pi would actually be 0 again. And if we did sine of 5 pi over 2, which is just 2 pi plus another pi over 2, that would be 1. Okay. So the point that I'm getting at here is that all of these numbers are larger than pi, and you see that at some point we hit -1 and 1, and that's going to repeat itself. So if we know that sine is going to bounce in between -1 to 1, then we also know that if we add 1 to sine here, then this is going to be 1 minus 1 here, 1 plus sine of x here, and 1 plus 1 here. Okay? And so, of course, this ends up just being 0. This ends up just being 2. So this means that here, if I did 0 over x squared, kind of build this back together here, I would have this situation where I'm just going to erase this part here, that my integrand is going to have values that vary in between 0 and 2 divided by x squared here. Okay, so we see here that this 2 divided by x squared this could be looked at as our big function, and our actual integrand can be looked at as our small function. Okay? So because of that, if we consider the integral from pi to infinity of 2 over x squared dx, which could also be rewritten this way, the important thing that we want to know is, does this integral actually converge or not? And since this number here is a number that is higher than 1, we know that this particular integral will converge. Okay? So since this integral converges, then that means 2 times that integral will converge. And thus, by the direct comparison theorem, we know that our original improper integral will also converge. So again, what that means is that if we wanted to go through the pain of actually figuring out what that actual value would be, we would be guaranteed to find a real number answer to that problem. Okay? Now, we may not be able to find out exactly what it is, but we can get close, depending upon what kind of techniques that we may have to use. But we know that there is a real number answer out there. Okay, and that's, again, I want to reiterate, that is the purpose of doing the direct comparison in the limit comparison test, because you want to make sure that if you want to go through the pain to find something, that you're actually going to find it once you're finished. Okay. All right. So with that being said, this concludes the video series on improper integrals. Thank you all for watching this video series. I do know that it was a lot, but I wanted to make sure that I had a lot of examples for you, and I covered this particular topic thoroughly because of the fact that it is very important as you move up to study higher mathematics. And so being able to have command over evaluating improper integrals, knowing when you need to even try to evaluate an improper integral and when not to even mess with it, is an important skill to have. It will save you a lot of time in the future. All right, take care.